All right. So we have now talked about what it means to find a matrix for a linear transformation. We walked through that process together. And what I want to do now is narrow the focus a little bit. What if the linear transformation that we're talking about is a linear operator, which again means that your domain and your codomain are the same vector space. In those cases, you don't have to do this, but typically, because we're using the same basis for the domain and the codomain, we would normally choose the same basis for each of them. So rather than B being one basis for V and B prime being some other basis for V, like in a change of basis kind of situation, we just choose the same basis. And in that case, instead of writing the matrix for T as T and then like two B's down here, we just shorten it to this. So it's a notational convenience. But when you see this, the matrix for T relative to B, it means it's using B for both the domain and the codomain. Okay, so that's very typical of linear operators. When we find matrices for those guys, we choose the same basis and we use this notation. I want to look at one linear operator in particular, one that we've talked about before, the identity operator. So if B is any basis for V, and I want to find the what do you call it? The matrix for that transformation, the matrix for I relative to our basis. What I'd like to show is that the matrix for our identity operator relative to B is always just the identity matrix. Not a huge surprise, hopefully, that the identity operator has the identity matrix as its matrix, but let's see why that's the case. So again, let's let B be the basis containing the vectors v1, v2 through vn, be a basis for V. Then, now let's think about the matrices for the linear operator. So I of v1 is equal to v1. That's what the identity matrix does, is it doesn't change the input. It gives us the same thing as our output, which is equal to 1 times v1, I don't need the parentheses there, I guess, plus 0 times v2 plus ... plus 0 times vn. Notice the only term that I need is the first one, and it's 1 times v1. What does this imply? Well, remember, for our transition matrix, we need to find the image of each of these basis vectors into this transformation relative to, again, B, because we're using the same basis for our codomain. So this would just be equal to 1, 0, 0, 0, 0, all the way down, right? And similarly, we can show that I of v2 is going to have as its coordinate vector. Think about what's going to be different here. This is going to map to v2, which as a linear combination of our basis vectors is going to look like 0 v1 plus 1 v2 plus and then zeros everywhere else. So this is going to give us this coordinate vector, 0, 1, 0, ... zeros everywhere else, right? And you're going to see this as a trend for all of these. So it's going to end at I of vn relative to B, which is going to give me this coordinate vector, 0, 0, ... all the way down to 1. Okay, so what does that mean for our matrix for this linear operator? Well, the matrix for I relative to B is going to equal the matrix that has these as its columns in this order. So 1, 0, 0, 0, all the way down. And then 0, 1, 0, 0, 0, all the way down. And then this continues. And the last column should be this guy, zeros, all the way down to 1. Okay, but we know that matrix, that is the identity matrix. It's the n by n identity matrix. And so that shows what we wanted to show. Now that makes perfect sense, because if you think about it, if I wanted to use this matrix to compute the image of some vector, then I know that I can do that by doing I of B times the vector v as a coordinate vector in B. But if this is just the identity matrix, that's I times v relative to B. And the identity matrix times anything is just the matrix it was multiplied to. So this is what we would expect to happen because we don't want the identity matrix to change anything. So the input, v relative to B, is the same thing as the resulting output, the v relative to B. It makes perfect sense that that's what would happen. Okay. All right, let's take a look at a couple of interesting theorems here. So let's let T1 be a linear transformation from U to V. T2 is a linear transformation from V to W. And I'm going to select these bases. And pay attention to the order of these bases. It's not necessarily what you would expect. B is the basis for U. B double prime is the basis for V. And B prime is the basis for W. You might expect these two to be in a different order. The reason I'm choosing this is because we're going to take a composition of these two linear transformations, and I want the result to be, or I want my matrix for that composition to be taking B into B prime. So I want this to have a basis for B, a basis B. I want this to have a basis B prime. B double prime is going to be the basis for this in between vector space V. Okay, if that makes sense. It turns out that if I want to find the matrix for a composition of linear transformations, and remember we proved a theorem in 8.2 that said that compositions of linear transformations are themselves linear transformations, so they should have their own matrices as well, because you can do this with any linear transformation. It turns out that this the matrix for this transformation is actually just the product of the matrices for the transformations T1 and T2 in this order, T2 times T1, same order that you write this composition in. Now, you notice I'm not proving this. Your book omits the proof also, but it's not hard to see why that is the case. If you look at this side, what do we use these for? Well, I'm supposed to take a matrix or a coordinate vector for some vector in U that I want to plug into this composition. And if I multiply this on the right by U relative to B, right, then this first product right here, this matrix times the coordinate vector for U, is going to give me the coordinate vector for the image of U under the transformation T1. So in other words, it's like plugging U into T1, which is what you do first in this linear composition. Then, because the result is the image of U under T1, and I'm multiplying that on the left by this matrix for T2, that's like taking T1 of U and plugging it into T2, which is the next step in a composition. So it makes perfect sense that this is what we would expect to get for a composition of two linear transformations. Here's what that actually means for us. Every single time you have multiplied two matrices together in this class, what you have actually done is you've taken the composition of two linear transformations. You just didn't know you were doing it. We've done lots of matrix multiplication for lots of different things, but every single time you can view what you were doing as composing two linear transformations. Okay, so that's kind of what I'm saying about this this section. Doesn't mean it's notationally convenient or computationally convenient or efficient to do this. It means that it opens up this whole world of theory that we've already developed that we can now start using for linear transformations. Second theorem, if T is a linear operator that maps V into itself, and if B is a basis for V, then we have this really useful equivalence. T is 1-to-1 if and only if the matrix for T is invertible. And not only that, if we have this, if T is 1-to-1, which makes this an invertible matrix, then because T is 1-to-1, it has an inverse transformation. But it turns out that the inverse transformation for T, its matrix is the inverse of the matrix for the for T relative to B. So that's again kind of trying to tie this into all the work that we've been doing. Every single time you've computed an inverse matrix for an invertible matrix or used an inverse matrix for something, what you've actually done is you've been working with an inverse transformation. an inverse linear transformation. But again, you didn't know you were doing that at the time. Now, that's what you've been doing. So this puts into context what matrix multiplication and inverse matrices actually are. All right, so we're going to wrap this up with one last example. Because we talked about compositions, I want to do an example where we use that result. So first thing I want to do is do a composition of these two linear transformations, and we have dealt with this composition before. This is a composition of two linear transformations that we dealt with back in 8.2 as an example. So T1 takes matrices in M22 into polynomials from P3, and it's defined this way. The matrix ABCD is mapped to the polynomial ax cubed plus bx squared plus cx plus d. We call that the natural isomorphism. Remember, we said that this is an isomorphism. And then T2 is going to take P3 into P2, and it's going to be the derivative operator that we've already dealt with. Okay, our goal here is just to find the matrix for the composition of T2 with T1 relative to the bases B and B prime, where B is the standard matrix for the vector space M22. We've seen this one before. B prime is the standard matrix for P2, which we've just used, 1x and x squared. And because the result that we just talked about requires a basis for this in-between vector space, which in this case is P3, we're going to use the standard basis for P3. So that's what B double prime is defined to be. All right. So in order to do this, remember, I need the matrix for T2 relative to the bases B and B double prime, and then I need another matrix for T1. So we've already found the matrix for T1 in a previous example. I'm going to work on the matrix for T2 right now. And in order to do that, I need to plug all of the basis vectors in B into this linear transformation to get the corresponding coordinate vectors relative to B double prime. So here's what we're looking at. T of 1, 0, 0, 0. T of 0, 1, 0, 0. T of 0, 0, 1, 0. Notice it's really important that we do this in the order that they're listed, because this is an ordered basis. Otherwise, your coordinate vector is not going to be correct. So 0, 0, 0, 1. What are each of these equal to? Well, again, what this does is it takes these entries and multiplies them as coefficients on this polynomial. So the only non-zero coefficient I have is a, which gets multiplied to a cubed in this first case here. That means I'm looking at 1x cubed, or just x cubed. Similarly, this will be equal to x squared, x, and 1. That's going to be the results of this. Notice, however, that these are exactly the vectors in B double prime. So just in reverse order. So if I want to compute this, let's go like this. If I want to find the coordinate vector for this guy relative to B double prime, what's that equal to? Well, 0, 0, 0, 1. Those would be the scalars on the linear combination that give me x cubed. 0, 0, 0, 1. What about this guy? 0, 1, 0, 0. Relative to B double prime. Easy enough to see that it would be, because it's x squared, and that's the third basis vector in my ordered basis B double prime, I'm going to have 0, 0, 1, 0. And you can kind of see the pattern here, right? So what does this mean for my matrix for T2 from relative to the bases B and B double prime? It's basically going to look like a reversed identity matrix, like this. That's 1, 0, 0, 0, like that. Okay. Now, let's do what we set out to do in the first place. I wanted the matrix for the composition of these two transformations. And we know that the composition of T2 with T1 relative to the bases B and B prime is equal to the product of these two matrices. So this is B double prime B times T1 of, this one takes, oh, sorry, I think I have this in the wrong order. That should be B, and that's B double prime. This is B double prime, B prime. If you ever get confused on a problem like this, what the order is supposed to be, you can think of these two inner bases as canceling out, and we should end up, I got this mixed up too. That should be B. That should be B prime right there. They should cancel out and then leave me with B prime B, like what we have here. Okay, well, we just found this matrix. This was equal to 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, like that. Okay? And then this is the matrix that we found previously, which was 0, 0. Let me make sure I have this one right. I don't want to mess this up. Yeah, 3 zeros. And then it was 1, 0, 0, 0, 2, 0, 0, 0, 3. Okay? So, oh, I think I have this in the wrong order. Yeah, sorry, I have this in the wrong order, huh? Because T1, which I just found, sorry, this is T1, so I have to reverse these. Let's fix that. Let's fix that. So here's what it should look like. It should look like 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3. And then that kind of reversed 4 by 4 identity matrix. Okay, what does this multiply to? Well, going through the matrix multiplication, I could see that this column times that row is going to be a 0. Multiply this column to that row, it's going to be a 0. This column to that row is going to give me 3. Okay, then this column, I'm going to get 0, 2, 0. And then this column to top row, I'm going to get 1, 0, 0. And then this column times each of these rows is just going to produce zeros for me like this. Okay, so it shouldn't be too surprising that the result is kind of, because this is like the identity matrix but reversed, the result looks like this matrix, but again, kind of reversed in the same way. This would be the matrix for the composition. Again, it's the result of multiplying the two matrices that we just came up with for the transformations that were used in that composition. Okay, it's pretty cool stuff. That's going to be it as far as what we need to cover in this section, and it's also it for what we cover in this class.